Hello and welcome to this last lecture of our course. And today we are going to discuss about the numerical solutions of ordinary differential equations. Now you may know that the differential equations that we study in mathematics are mainly classified into two categories. One is the ordinary differential equations and the partial differential equations, right? The ordinary differential equations involve ordinary derivatives like dy dx or dx dt, like that, ordinary derivatives, and the partial differential equations involve partial derivatives, like this, right? The partial derivatives. But in this lecture we are going to discuss about only the ordinary differential equations, and to solve them we are going to follow two methods. The first one is the Euler method and the second one is the Runge-Kutta method. Okay, so let's first discuss about the Euler method. What is Euler method? This is the simplest method for solving any kind of differential equation of this form, right? So this is a first order differential equation, ordinary differential equation, and this is the simplest method, this Euler method. So here is an example of a first order, a linear type differential equation. This y is the dependent variable and this x is the independent variable. And here what is the meaning of this linear? The meaning of this linear is that there is no terms like y square or y cube in the differential equation present. Only dependent variables of the order y to the power 1 is present. If you have terms like y square or y cube in the differential equation, then that will become a non-linear type differential equation, right? So this is a first order linear differential equation, and this method can also be used to solve second order type differential equations. What do you mean by second order type differential equation? In second order type differential equation, there will be the double derivatives will be present. The double derivatives of the dependent variable y will be present, right? And what are some examples that we usually encounter in physics? This example, this first example, is the equation motion of a particle executing SHM, and this is also another example. This is the differential equation of a pendulum, right? A pendulum executing oscillating around an equilibrium position, right? So this describes the motion of a pendulum. And this is a non-linear type second order differential equation. Why? Because as you know that the sin x can be expanded in the Taylor series, and if we expand it, sin x will be like this: x minus x cube by 3 factorial plus x5 by 5 factorial, and so on, right? So that is why this dependent variable x here has terms like x to the power 5, x to the power 5, x to the power 3, and so on, right? So that is why this is a non-linear type differential equation. Now if you want to convert it to a linear type differential equation, you have to assume that sin x is just nearly equal to x, right? So you are ignoring these terms, and when you can ignore these terms, when this x is small, when this x is very small, or the amplitude of the oscillation is very small, you can ignore all these terms, and then sin x will be nearly equal to x, and in that case this non-linear equation becomes this linear differential equation, right? So the linear form of this differential equation is this differential equation right here, right? So this is the exact equation, but But when we solve problems, we usually assume that sin x is nearly equal to x only, because we are dealing with only small amplitude oscillations in physics. So that is why we use this approximation. But the exact equation that describes any oscillation will be this, right? So these are the examples of linear type second order differential equation and non-linear type second order differential equation. So these second order differential equations can be separated into two first order differential equations by introducing a new variable. For example, here, so these second order type differential equations can be separated into two first order differential equations by introducing a new variable. For example, here, this dx by dt, you can write it as y. Introduce a new variable y. So if you write this dx by dt as y, then what will be the double derivative of it? It will be just dy by dt, right? So then this dy by dt will become minus omega square sin x, right? So here you started with a second order differential equation, but here you have two first order type differential equations that exactly describe this equation. So these second order type differential equations can be separated into two first order type differential equations, right? So these two are first order type differential equations, but they actually represent this second order type differential equation. Hence we need to learn the numerical solutions of first order D's only, right? If you know the numerical solution to first order differential equation only, you can solve the second order and the higher order differential equations itself, right? Because you can separate all the higher order differential equations into first order type differential equations. You don't need to learn about the second order differential equations separately, right? Just learn how to solve the first order differential equations. Then by using them, you can solve any higher order differential equation, right? Make it clear that if you learn only the first order differential equation, you can solve any other higher order differential equation, because you can separate any higher order differential equation to a series of first order differential equations. Okay, so now let's understand how to use the Euler method. So the Euler's method to solve this ordinary differential equation of the form like this. This right hand side part can be anything, right? For the example, it was like y plus x square, like that. So if the differential equation has the form like this, then how to apply the Euler method? It is explained below. So the slope at point xi can be estimated as, so first you have to find, to use the Euler method, the slope at this point xi. Okay. Suppose this is the exact solution of the differential equation. The solution of the differential equation dy by dx is equal to f xy. The exact solution is this. Then at this point xi, what will be the slope? Slope at this point. Then that will be dy by dx at that point, and you can write it as yi plus 1 minus yi divided by xi plus 1 minus xi. So this is the point yi, and this is the point yi plus 1, and the slope at this point will be this length, right? This length divided by this length. Suppose this h is an arbitrary step size, right? And this can be estimated as this slope can be estimated as this discrete form, right? And this xi plus 1 minus xi is actually h, where h is the xi plus 1 minus xi is the step size, right? So this slope estimate usually the derivative actually represents the slope at a point for a function. So dy by dx can be represented in this way, right? You choose any arbitrary step size. It must be a very small number, right? And choose another point near to this point xi, where you want to find the slope, and find the value of this find the value of the function at this point xi plus 1, and as usual apply the dy by dx, right? This is actually the delta y by delta x, not exactly dy by dx, right? Or you can write it as delta y by delta x. So delta y by delta x will be can be estimated in this way, right? This is delta y, this part is delta y, and this is delta x. And when you take this limit delta x to 0, this delta y by delta x will become dy by dx, right? The as usual concept of derivatives. I hope you are familiar with it, and yeah, so that is how you can write. Now by substituting this equation 2 in equation 1, we get, let me write it back because we are just approximating it, right? Just an approximation that dy by dx is actually equal to delta y by delta x. So here if you substitute this equation 2 in equation 1, means this equation 2 in equation 1, the value in the place of dy by dx, put it here, right? Then you will get yi plus 1 is equal to yi plus h into f xi yi, right? So this is known as the Euler's method, or this Euler's formula, and this can be used recursively to evaluate y1x, y2x, and starting from the initial condition that yx0 is equals to y0. So these are all used to solve initial value problems, right? You may know that there is a difference between the initial value problem and a boundary value problem. So these methods, the Euler method, the Runge Kutta methods, they are all used to solve the initial value problems. The initial value problems, right? So this Euler's formula can be used recursively. If you know the value y0, then you can use it recursively to find all this y1, y2, y3 and so on up to the desired point, right? So note that what this formula represents, that this new value of this function is actually the old value that you have from the initial condition, plus slope, right? Slope, this is nothing but this f xi yi is nothing but the slope dy dx into the step size. The step size is h. As shown in the figure, the solution in the figure, the solution error varies directly with the step size h. Higher order higher solution Accuracy is obtained by using a smaller step size. If you choose your step size to be small, then you may get a more accurate result. So if you are unable to follow all this, just the Euler method is just simple. I may write it like this. Suppose dy by dx is some function f, right? And suppose this is f of xy, and this f of xy may be in the form like this, x square or y or something like sin x plus y or like that, right? Any function is present, or any non-linear function is also present, doesn't matter. So here what will be dy? Dy will be f of xy into dx, right? Then if you know any initial value, suppose you know the value of the function y(x0) at the value of the function at some initial point x0, and the value is y0, then what will be the value of the function at a point y x0 plus dx? This dx is the step size. Then what will be the value of the function at a point y x0 plus dx? The value will be this y0 plus dy, right? And what is this dy? Dy is this, means y0, and dy will be f of x0 y0 into dx. This is y x plus x0 plus dx. Right? And this is exactly the Euler's formula, right? Very simple. Thus, just take this dy as f of xy into dx, and this is the increment in the function y, right? What is a very small increment in this function y? This dy will be like this. So y x0 plus dx, a small increment in the function will be y0 plus dy if you have an initial value, and then this will be y0 plus f of x0 y0 into dx, right? Where this dx is the step size h, and this is the slope, and this is the initial point or the old value, and this is the new point, and this is the y I plus 1, and this is yi, right? Yi. So that is how the Euler method works. Okay, so that is all about the Euler method. Now let's discuss about the Runge-Kutta methods in brief. For this Runge-Kutta method, we are not going to derive the formulae because they are very lengthy to derive. So here I am just going to give you a brief idea about the Runge-Kutta methods. So these Runge-Kutta methods are very important from numerical analysis perspective because they are used heavily. So this in numerical analysis there are several type of Runge-Kutta methods to solve the initial value problems, and they are all based on a one equation, and this equation is nothing but the Euler's formula, where this m is the slope, right? yi plus 1 is equals to yi plus m into h. This m is the slope, right? So this where this m represents the slope, that is the weighted average of the slopes at various points in the interval h. So what we did in the Euler method, we calculated the slope at only one point in the interval. In the interval x I to x I plus 1, we calculated the slope only at one point in the interval, right? But we can calculate the slopes at different points in the interval, at more than one point in the interval, and that will give you a more accurate result. So what you need to do, I'll show you here, right? Here you show that we calculated the Euler method, we calculated the slope at this point only. But what we can do, we can calculate also the slope at more than one point, and then take their weighted average by giving them some appropriate weight of that slope, and then take their average, right? The weighted average, take their weighted average of these slopes, and then you will get a better approximation for this function, right? The slope is, so here you see that the exact solution is like this, but here the approximate solution here is like this, right? Because you are taking this dy by dx as this, but this dy by dx is actually this function, and in the Euler method we are taking this dy by dx as this line only. So that is why there is a large error in this Euler method. But you take more than one slopes inside the interval, you will get a more approximate, more accurate function that will represent the exact solution, and the error will be less, right? So this Runge-Kutta methods is actually based on a method that will take more than one slopes in the interval h, right? So if we estimate m using slopes at r points, at r number of points we are taking the slope in the interval x I to x I plus 1, then this slope m will become omega 1 m1, omega 2 m2, up to omega r mr, right? This m1 is the slope at point 1, and this is m2 the slope at point 2, mr the slope at point r, and this, what is this omega 1, omega 2, omega r? These are the weights, right? Omega 1, omega 2, omega r are the weights, and the weights of the slopes at various points, right? And if you want a complete derivation of these weights, what are these weight numbers? You can search for it in the book, right? In the suggested book you may find it. So the slopes m1, m2, mr are computed as follows, right? So here I have written this formula. You don't need to worry about them. So here this is m1 and this is mr. So note that the computation of any slope at any point involves the slope at all previous points, and slopes can be computed recursively using the equation 2 from this m1 is equals to fi xi, right? So you don't worry about them, ignore them. So the Runge-Kutta methods are known by their order, right? For instance, this RK method is called R order Runge-Kutta method when slope at r points are used to construct the weighted average of slope m, right? When r is equal to 1, we use only one slope at point xi yi to estimate yi plus 1. This method is known as the Euler method, and this is also the first order Runge-Kutta methods. So as I have mentioned that you are going to use slopes at different points, and if you are using only one slope at a single point, you are not using more than one point to find the slope, then that is obviously the Euler method, and this is also the first order Runge-Kutta method. Now if you choose 2 points to find slope in the interval xi to xi plus 1, then that will be Runge-Kutta method of order 2 or second order Runge-Kutta method. Then similarly, if you choose 3 points in the interval, then it will be third order Runge-Kutta method. Then if you choose 4 points in the interval, then that will be the fourth order Runge-Kutta method. And we usually use the fourth order Runge-Kutta method, the RK4 method. The RK4 method is the most important one, right? So here so here you are using, so what is this M1? M1 is the slope from the Euler method, right? Here this M2, M3 and M4, that is how you solve this slopes, right? If you are using M1 and M2, then it will be known as the second order Runge-Kutta method. If you are using M1, M2, M3 and M4, it will be known as the fourth order Runge-Kutta method. And you are using slopes at 4 different points, right? So this so we are discussing about the Euler method, and the Euler method is also known as the first order Runge-Kutta method. In the Euler method, this is the formula, and this is slope at only 1 point, and S is obviously the step size. Now that is how I am also discussing here how to solve a second order type differential equation that I have already mentioned here before, right? To solve a second order type differential equation, you need 2 initial conditions, and you need to separate them into 2 differential equations, right? And 2 differential equations, and for this differential equation this will be the Euler method, and for this differential equation this will be the Euler method, right? The exact same formula, that for this differential equation this u is your new variable, right? So this will be yi plus 1 be equal to yi plus h into yi xi yi, and this for this du dx, it will be ui plus 1 is equal to ui plus h into this step size is also there into this f xi yi ui, right? So there are these 2 differential equations of first order, right? We converted the second order type to first order type and solve them individually using the Euler method, right? So that is how you solve by using the Euler method. And similarly, now if you want to find the RK2 method, if you want to use the Runge-Kutta method of order 2, then you have to use slopes at 2 points. Here you have to use M1 and M2. And what are these 2 points in the interval xi to xi plus 1? The 2 points will be xi and xi plus 3 by 4h. So you are finding the slope at 2 different points now, xi and xi plus 3 by 4h. Why 3 by 4h? That you will understand if you follow the derivation of it. But here I am not going to describe the derivation because time is limited. So you may go through the book. The derivation is very simple, and that is not very complicated. So here you are trying to find the slope at 2 different points and take their average, right? And that will be your slope. And if you know the average slope, the yi plus 1 will be yi into m into h. Again use the same formula. Just thus the difference in the Runge-Kutta method is that this m is not a ordinary slope, it is the weighted average of slopes at different points, right? I hope you are getting my point. this m in the Runge-Kutta method is different from the m in the Euler method. This m in the Runge-Kutta method is the weighted average of slopes at many different points inside the interval. Right? Remember that. So there, these are the two points where you are calculating the slope, and this will be the weighted average. The weight of this m1 m1 slope will be 1 by 3, and the weight of this slope m2 will be 2 by 3. Right? That is how these weights of the slope are there, and this is known as the second order Runge-Kutta method or the Heinz method. Right? These are the weights. Set. These are the weights of the slopes m1 and m2. So this is known as the second order Runge-Kutta method, where you are using slope at two different points. Then there is something also known as the modified Euler method. In the modified Euler method, you find slope at the initial point and the final point. Right? So here you are finding the slope at initial point and the final point, and then take their average, just average, not the weighted average, just simple average, and put it here in the place of slope. This is known as the modified Euler method. So here you put xi, yi value, then here you put, to calculate k2, you will put xi plus h and yi plus k1h. Right? The function you know, the function will be given from the differential equation. Just in the place of the function, you don't need to know the derivation. Just know this formula and know this simple concept, what you are doing here. Right? The function will be given to you, dy by dx will be some function f of xy. So to find k1, put the values, initial values, x0, y0. Right? Then what will be k2? From the initial point, it will be f of x0 plus h, and here it will be y0 plus this k1 into h. Right? In the place of x and y, just put these values, x0, y0, and x0 plus h and y0 plus k1h. The k1 is obviously this. Right? So just put these values in the function, and you will get your k1 and k2 and compute the result. You don't need to know the derivation exactly, just know the concept. So far in the above discussion, we get that it is possible to construct RK methods of different orders. However, the commonly used ones are the fourth order methods. Right? Although there are different versions of fourth order RK methods, the most popular one is the classical fourth order Runge-Kutta method as given below. This is the classical fourth one, Runge-Kutta method, that is yi plus 1 will be equal to yi plus this weighted average of slopes at 4 different points into the step size. So this is the m. This is the m. The form is same, just the m is different. So here this m is the weighted average of slopes at 4 different points, m1, m2, m3, and m4. And what are the weights? The weights are like this: 1 by 6, 2 by 6, again 2 by 6, and again 1 by 6. Right? These are the weights at the points M1, M2, M3 and M4. Right? And how to find this M1, M2, M3 and M4? The formula is written here. Just put this formula in your code and solve it. You don't need to do those large derivations. So M1 will be f xi yi, then M2 will be f xi plus h by 2, then comma yi plus M1 h by 2, then M3 will be again at the point xi plus h by 2 and yi plus M2 h by 2. Then the last slope will be at the last point of the interval. M4 will be xi f of xi plus h comma yi plus M3h. Right? That is how you need to find all these slopes and put the formula inside this M1, M2, M3, M4 and find yi plus 1 recursively. So like this Euler method, you can also use this RK4 method to solve the second order type differential equations. Suppose this is your differential equation with the initial conditions given to you, right? The initial condition will be like this. One is the y x0 will be y0, and this y dash x0 is the derivative of the function at the point x0, and it will be y dash 0, right? So you need to solve that, and so you need to introduce a new variable. So assume that dy by dx will be u, and solve for this, right? This yi plus 1 will be equal to yi plus h by 6, and these are the slopes, right? Then again du by dx will be f of x y u, right? Because this is the differential equation, that is the double derivative of the y is f. So here this du by dx will be f of x, y and u. So this u I plus 1 will be ui plus h by 6, and this j1, j2, j3, j4, right? What is this? What are this? K1 is ui, and K2 is, right, the K2 is ui plus h j1 divided by 2. So suppose this is j1, right? And then this will be j2, and then this will be j3, and then this will be j4, right? So this j1, j2, j3, j4 from this are found from the Runge Kutta methods, right? Because here you know the function, so as it is getting a bit more complicated, I'm erasing them, right? So what are these j1, j2 and k1, k2 values, right? So as you know that here, this is the differential equation. This is the first differential equation, and this is the second differential equation. And how to solve this first differential equation using the RK4 method? For in this K1 will be here, it will be u x0 y0, right? And this u x0 y0 is actually not, you don't actually have it really, because you don't know this variable, right? You don't know what is the value of y x0 y0 because you are introducing a new variable, right? So that is why you need to choose this k1 as ui, right? Then this k2 will be equal to ui plus h j1 by 2. This is the j1 value, j2 value, and then it will be like this, right? So this, so here is something a bit complicated, right? Because as you are solving these two equations simultaneously, right? As you are solving these two equations simultaneously, here this uh, u variable and this y variable, right, are there, and okay, so here it is a bit complicated to explain, right? So let me go through the code, and then I will explain to you what is happening here, how to solve this second order type differential equation using those RK4 method, using this RK4 method. When you see the code, it will be more clear. Okay. The problem is that the problem is that here there are three variables, right? X, Y, and U. But here you have discussed it for only two variables. So what is this K1? These K1s uh, are the values, are these values. They don't have these yi values, right? So this K1 will be like this. First you have to find what is K1, and then from that you will find what is J1. Okay, so let me show you the code, and from that code it will be more evident what is happening here. Okay, let me go to the code. Let me stop presenting here. Sharing, and here let me share. Okay, so let's discuss about the RK4 method, and here we are trying to solve this differential equation. This is for anharmonic type oscillators. So here this you may see that if you consider only terms like minus omega square x, that will be your familiar type linear linear differential equation for simple harmonic motion. But What if you consider more terms like this minus alpha x square and beta x cube, then the differential equation will be like this. This is a anharmonic type differential equation. This is the anharmonic oscillator. This is not a harmonic oscillator, right? The harmonic oscillator has a differential equation like this only, up to minus omega square x. But if you add more terms like alpha x square and beta x cube, this will be a anharmonic oscillator, right? So let's solve it using the Runge-Kutta 4 method. Now you have to define this. If this is the differential equation, then what will be the f of x y or f of x t? Here there will be three variables, t, x and v, where t is for time, this x is for position and v is for velocity, right? So this f t x v will return minus omega square x minus alpha x square minus beta x cube, right? So what we are doing here, we are writing this differential equation into two separate differential equation. The first differential equation will be dx by dt will be equal to v, right? Dx by dt, let me write here, dx by dt, let me add as comment that dx by dt, you have to separate them into two differential equations, dx by dt equals to v, and then what is the next equation? dv by dt will be equals to what? This f of t x v function, right? So first you have to separate this differential equation, that is the double derivative. This double dot represents the double derivative of the x with respect to time. So this double derivative of the x variable will give you this function here. So first you have to separate them into two differential equations. So dx by dt will be equal to v, and dv by dt will be this function here, this function, right? That is, this is in terms of three variables, t, x and v. Why v is present there, I will explain it later. So here first it is it is a function of x only, right? So minus omega square x minus alpha x square and minus beta x cube. So value of omega 0 is 1, then a and b is present here, and ti is there. This a is the alpha and this b is the beta, and omega 0 is this w0 is this omega 0 value, right? The frequency, the angular frequency of oscillation. Then x0, the initial amplitude is given to you. Then v0 value is also given, the initial velocity. The initial amplitude and the initial velocity, the initial conditions are given to you. And then this t initial or t final is also given to you, right? The initial time is 0 and this t final is suppose 30 seconds, right? Then the number of points inside the interval is 1000. Then the step size will be tf minus ti divided by n, right? This will be the step size, as there are 1000 number of points inside the interval. So this will be t equals to ti, then x equal to x0, then v equal to v0. Start the parameters. The initial parameters are given as entry to t, x and v variables, right? You are giving the initial values as the starting point to these parameters, time, position, velocity, and also create a list to store this data as we increment through the function, and then we will plot the data using this list, right? So you need to store this data, so that is why you are creating this list. Now here this RK4 method is starting, right? So first you have to find what is K1. K1 is actually V, the initial velocity V. Then this J1 will be f of Tx V, right? And what is this K2? K2 will be this value, this V value, the initial point, plus this H star J1 divided by 2, right? That means if there is only one variable present in the Runge-Kutta method, so just this will be the form, right? This J1 is the slope at that point, at that initial point. So this V will be the slope at the next point will be K2 equal to V plus H star into J1 divided by 2. Then what will be J2? J2 will come from the Runge-Kutta method formula, right? For 3 variables, and then K3 and then J3, right? The K3 value will be like also this. It will come from the J2 value, and J3 value will be like this, and similarly J4, right? And K4 and J4. Similar to X, it will give you the values, right? You see that this V entry here does not have any meaning, or this T entry here is also doesn't have a meaning, because here this is only in terms of X, right? This function is only in terms of X. This T and V is not present, but we are writing it for sake of convenience, for sake of to understand it better, right? This T plus H and this V equal V plus J3H, that is not present in the function, right? Only X is present in the function, but we are still writing them for the sake of convenience, right? Then this will be X, right, using the Runge-Kutta formula. Take the weighted average of all the slopes at 4 different points, and then add them together to the list, right? Append them to the list at every step. So you are using this T equals T plus H. You are increasing the time value using the step size, and then print them, and you will get the solution, right? And this is the solution of the anharmonic type differential equation. Similarly, you can also create the solution for the non-linear type differential equation. And these are there, you may go through them and learn how the solutions are changing. Then there are some more examples here I have written for the forced linear harmonic oscillator. Like this is the solution. For a simple linear harmonic oscillator, this is the solution. This is the phase space, and this is the damped harmonic oscillator solution. Just play around them and see how they are behaving with different parameters, right? So this Runge-Kutta method is bit difficult to understand, but you may just use this formula. Don't worry much about the details. Just use this formula to solve it. Right? For this, so the problem is that in this second order type Runge-Kutta method, for this first differential equation, right? For this first differential equation, there is only one variable, and for this second differential equation, there is these three variables t, x, and v. So first, when you are calculating k1, it will be just vi or ui, right? Using your formula. Then this k2 will be v plus hj1 divided by 2. So this is the slope at that point, at that initial point, right? So that is why it will be like this, because there is only one variable. Then k3, then k4 is also like this, and then j1, right? Using for the j1 you are this is the initial point, and then for j2 you have to also use the values of k1, right? This k1 value is also is present here, and j1 value is also present here, right? So this, so you are incrementing the x, the position using this k1, right? But you are incrementing this velocity using these j1 values. Similarly here, you are incrementing again the velocity again, then you are incrementing the position using the k2 value, and incrementing the velocity using the j2 value, right? And similarly here you are incrementing the we are finding the k4, and here it will be j4, and here the incrementing x using the k3 value, and v value using the j3 to find k4 and j4, right? So the thing is that there is only one variable for this first differential equation, and there are these three variables for the second differential equation, right? So that is why this change in the Runge-Kutta method is appearing, but the concept is same. The first variables, right, this t is the first variable. They will change like this. Yeah, right. This t will, or the v will change like this to find k1, k2, k3, k4, and the next variables like x or v, they will change like this. This x will change like this using k1 values, and this v will change the value, update their values using the j values, right? And if there are more than this, suppose there are a third order differential equation, then how to use this Runge-Kutta method? Then there will be this k1, j1, and suppose another value m1, right? There will be another value m1 if there is a third order type differential equation, right? And that will be more complicated to solve now. So what will be m1? If there is a third order differential equation, this m1 will become suppose this is v, and suppose this j1 will be some another constant, suppose h or not h, suppose p, then this m1 will be f of txv, or not f of txv, it will be like this, f of t x, this v and p. There will be now 4 variables inside that function, right? So that will be how that will again how you will proceed, right? So that is the Runge-Kutta method, and here we are solving using the Euler method. The Euler methods are simple. Suppose you are solving this linear differential equation up to just omega square x, right? Here the function will be like this, and here are the initial conditions, here your step size, and here you are defining the parameters, and here define the list, and then there is a Euler method that x will be equal to x plus h into v, and v will be like this, right? So this h is the first differential equation. As this is a second order type differential equation, you have to convert it into two first order differential equation. For the x it will be like this, and for the v it will be like this, right? And update the time values and append it to the list, then you will get your solution. Now if you don't understand anything, you may ask later. If you are not getting this RK4 method or this Euler method, you may ask me personally. I will help you out. Okay, so that is it for today, and this is the end of this lecture. And this is also the end of this course. If you have any doubt in any lecture, you may send a message. I will definitely help you out. Okay, so that is it for today. Bye bye. Bye.